I am delighted to introduce our seminar speaker for this week, Dr. Kim Baraka. Dr. Baraka is an assistant professor at VU Amsterdam. His interests are in the intersection between AI and HRI, and in particular, the interactions of teaching and learning between humans and robots. If he looks familiar, it's because Kim was here at Carnegie Mellon. He has his PhD in robotics from CMU and from IST in Lisbon as part of the CMU Portugal robotics program. And after that, he joined UT Austin briefly for a postdoc. And on a personal note, I was on Kim's committee, and so it's really fun to see him back here as a fully grown professor giving a seminar talk. He does really interesting work, and he's an artist as well as a roboticist, and so he brings that creativity to all of the work that he does. And so I'm excited to see what he has to share with us today. So welcome our speaker.
Thank you, Henny, for the wonderful introduction. Thanks for all of you who came on this sunny afternoon. Today I'd like to share with you a little bit of my vision on the research that I plan to do in the next few years and some of the stuff that I have been doing over the last 3 years. So as you may have seen already, the title of my talk is Why We Should Build Robot Apprentices and Why We Shouldn't Do It Alone. And hopefully by the end of this talk, you'll get a bit of a sense of why I think this is a good idea, why this is a good way to go for the field of HRI. So a little bit more details about my background. I started out as an electrical and computer engineering student back in Beirut, where I grew up. And it was, as a young teenager, I was actually very interested in physics. So I went to CERN in Switzerland to really make sure, do I really want to do this, yes or no? And it didn't turn out quite well with my career in physics, and I instead switched to robotics. So came in 2014 to this very building to do my master's in robotics, and then continued to the PhD, as Henny mentioned, between Portugal and CMU. In that PhD project, I worked mostly on socially assistive robotics, specifically in the domain of autism. And I worked mostly on algorithms that could enable more efficient and more appropriate interactions in these healthcare contexts. A very short postdoc in the Socially Intelligent Machines Lab in Texas, which then led me to the Netherlands, where I am right now, for the last 3 years working as an assistant professor in the social AI group. As Henny also mentioned, I'm also a dancer. By training, I've been dancing most of my life, professionally for the last 15 years. And I continue to teach, perform, and also research movement and dance, and this whole world that is movement and improvisation specifically. This is the space upstairs that you might recognize. Some of you may or may not. If you don't know it, then you should check it out. It's a really cool space in Pittsburgh that does a lot of things at the intersection between different performing arts forms. A little bit more background on some of the stuff happening in our university in the Netherlands. So we are one of 2 universities in Amsterdam. We have a computer science department that has an AI section, so a section specifically dedicated to AI research, which goes all the way from knowledge graphs to things like human-robot interaction. The group that I'm part of is called the Social AI Group, where we're interested in researching and developing what we call smarter digital companions, which could be social robots all the way to chatbots and other interventions through different types of agents. And our mission is to advance AI to improve the way that humans and machines understand and interact with each other. So, as you probably already guessed, I'm interested in the intersection between these 2 spheres. And I believe the spark really lies in 3 things. The first one is obviously interaction, but I'm specifically interested in problems of learning and problems of teaching in this particular context. Now, to be able to do research at this intersection, there's a couple of things I need to, at least know about on the human side and on the robot side, so outside this intersection. The first one is, basic theories about psychology, human factors, cognitive and behavior modeling. But I'm also interested in bringing things like the performing arts to my practice. On the robot side, I'm interested in, obviously, in AI techniques that are moving very fast, specifically machine learning, and also potentially mechanics and control. So the stuff that I don't always talk about is that 100% of my research is inspired by dance problems. But I don't often say this because it might not be relevant to everyone, it might not be even relevant to anyone else but me, but sometimes it is and sometimes it's not. So this is just one slide to let you know that everything that I will talk about today is secretly inspired by dance, even though it might not be very clear how it is. So, I ask questions to myself sometimes like, how does a choreographer instruct a dancer? How does a dancer think or behave in a highly dynamic and highly collaborative environment? And how can these be translated into HRI, such as how can a robot learn from what I would call a choreographer/user, who is trying to program the robot to have a certain behavior? Or how can a robot engage in a dance with a user? So today I'd like to tell you a story, and there's a bunch of characters in the story, so I'm going to go ahead and introduce them one by one. The first one is obviously the robot, right? This physically embodied agent that is programmed to achieve a task which may or may not involve humans. The second character is the environment, which we often think about as uncertain, dynamic, and may or may not include humans. Third character is the developer. So the developer is the person, usually a team, that programs the behaviors or the intelligence of said robots. And I want to highlight that this is a team or an individual that is a human, right, or a collection of humans. And then we have the end user. Right? So this is the person who actually gets to interact with the robot at deployment time and gets to benefit from the things that the robot does, hopefully for them and with them. And there's a bunch of things that I can list here, but I'll just summarize them by saying, is a human. And it'll become clear what I mean by that in the next few slides. So before I jump into the details of the story, I'd like to quickly mention a consortium that is currently funding some of the research in the Netherlands. And this is called the Hybrid Intelligence Center. It's a consortium across 6 or 7 universities across the country that is really interested in studying these coupled systems between AI and humans. So human, artificial, hybrid intelligence systems. And these range from collaborative annotation tools all the way to robots performing surgery with surgeons, for example. And we're interested in modeling these at different levels of abstraction, from high-level team dynamics like we present in this paper, all the way to the lower level stuff like the basic building blocks such as theory of mind and intent recognition. So the story goes like this. We have a developer that is thinking really hard about designing a system, mainly a robot, that's going to be interacting with the environment and with the user. And this developer has assumptions at development time that we would love for them to match reality at deployment time, right? So this is what we wish for. The reality, the hard truth, is that the world is extremely diverse. And I'm sure a lot of you have seen the example of all the door handles that exist in the world, a classic example for robotics. I'm showing similar examples for kitchen tools that you may have never seen before. The second hard truth is that the world is non-stationary, right? So you may have a robot that is going around in your kitchen, and then you decide to remodel your kitchen, and probably the robot has to somehow adapt to this new situation here. Third hard truth, which is hard for the robot, but obvious for us, is that the world contains people. And that these people are extremely diverse and have an enormous range of preferences and needs that the robot needs to keep in mind, or at least that the developer needs to keep in mind. So the hard truth is that these two do not often match. So how do we deal with this hard truth, right? From the technical advances perspective, there's been a lot of work on foundational models, specifically for robotics, right? Trying to address things like diversity, uncertainty, etc., and trying to have these kind of general purpose solutions to solve a wide range of problems without having to fine-tune it, or at least without having to specifically program it for every case. What I want to argue in this talk is that regardless of how performant these foundational models or any sort of technical solutions will be, I strongly believe that pre-programming or pre-training will never be enough, right? And this is for the reasons that I presented before. And I believe that the real grand challenge of robotics is this umbrella term of adaptation, which I understand as applying, combining, and transferring knowledge in novel tasks and novel situations. So how do we go about this? There's two ways to go about this. The first one is to do this adaptation completely autonomously. Right? To have a robot that is able to, without any human intervention, figure out how to optimize its own policy or its own behavior according to this novel situation and this novel task. The problem is this is potentially unsafe, right? For the robot, for the environment, for potential humans in the environment, and it's highly inefficient, right? So if you think about reinforcement learning in the real world, that's extremely inefficient, requires a lot of trial and error. The other option is to involve the human in the loop. So what are some of the advantages of involving humans? Well, first of all, we could leverage domain expertise, right? And by domain expertise, I don't necessarily mean that we're going to work with experts at, professional, like surgeons and whatnot. We, as lay people, are domain experts at our own environments. We're domain experts at how we want the robots to behave and act in the world that we live in. Humans can accelerate learning, can guide exploration, can potentially avoid unsafe behavior, and most importantly, they can personalize the robot's policy or the robot's behavior according to their own wishes and preferences. Now, this doesn't come without some challenges, right? The first one is that, well, if you let humans influence how the robot behaves in the world, you might get less control as a developer over potential unintended uses of this technology, right? Another one is that this could be potentially inconvenient for users, that we're putting the burden on them to be able to kind of fine-tune these behaviors or teach the robot certain behaviors. So despite these shortcomings, I strongly believe that if we want to have robots that are able to carry out tasks effectively, according to user expectations, and potentially acquire new skills over time, we have no other options than involving humans in the loop. And I would emphasize not just humans in the loop, but humans on the loop, humans as part of the loop. So where do we start? So there's amazing work in interactive machine learning that tries to involve a human in the learning process of an agent. I'm sure a lot of you have learned about or have known about learning from demonstrations, right? It's been around for a long time. Learning from evaluative feedback, right? So, thumbs up, thumbs down kind of thing. Advice, which is about the action the agent needs to take. Corrective feedback, ranking, and the list goes on. There's a number of tools that allow us to do certain things like that, where the human is helping the agent learn a better policy. More recently, there's been a lot of interest in using large language models to create better policies through interaction with users. And so this is an example from DeepMind from a few months ago, I believe. Carolina Parada at HRI gave a keynote about this, which was a wonderful keynote, on how these natural language instructions can allow these robots to learn better policy just by interacting with users about 5 or 6 times. That dramatically improved the learning in these complex manipulation domains. What is the problem with these approaches? I would argue the main problem with these approaches is that they equate human with source of useful information. And I want to argue that humans are more than that. I want to argue that humans are actually a source of rich know-how that is communicated both through explicit and implicit signals in the context of an interaction. So not removed away from that context and that interaction. So to address this problem, some colleagues and I have been thinking a lot about how do we define this set of problems that thinks of it in that particular sense. And we came up with this term that we call human interactive robot learning, or HURL for short, where we're thinking about all these different ways that robots can learn through interaction with the humans. So I'm defining HURL as the collection of settings and methods where a robot is learning through interaction with a human. So what are some minimal assumptions for such a problem? The first one is that, well, you obviously have a robot that is executing a task, right? The second assumption is that this robot gets better at the task as a result of that interaction. So there's a causal relationship between the interaction with the human and the robot getting better at the task. We also assume that whatever the human acts or communicates influences what the robot does. So that's kind of clear. It's kind of a, it's part of A2. But we also assume that whatever the robot does also affects what the human does, right, in terms of decision making. And so what this does is that it puts interaction at the forefront of this problem, right? And it acknowledges the human as more than just a data source. It acknowledges it as an agent that is adaptive, right? Adapts and co-learns with the agent. Non-stationary, can potentially change their mind in the middle of the teaching, right? Or get better at teaching. Non-optimal, resource limited, and the list goes on and on and on. We're currently writing a vision paper about this, thinking about how do we frame this problem and how does it relate to existing pockets of work in different fields. So the image that I would like to use here, and this relates back to my title, is thinking of a transition from robots as tools, where they're limited in scope, they have a fixed performance, they are passive most of the time, seen as a means to an end by users, often impersonal and seen as an extension of oneself, into something like this, closer to this, I would say, where you have robots as apprentices that can learn from people and people can potentially teach robots. So what does this bring us? This brings us a robot that can potentially grow in scope, right? That can improve performance over time, that is potentially more active in that process, that can be seen as more than just a means to an end by the user, right? Potentially, things like social bonding might occur between the robot apprentice and the human that is teaching the robot. And this may or may not something we actually want. And then finally, it makes it more personal, and it makes people see it more as a teammate rather than a tool. So I did not invent this metaphor. This is a metaphor that has been around for a very long time. In 1995, Adrian Stoica published a PhD thesis on motion learning by robot apprentices, and this was kind of early work that then developed the field of learning from demonstrations. So what do I mean by robots learning and interaction? How does this look like? So what I'm showing here is an example of task where I think that I think illustrate well what I'm thinking about when I'm thinking about human interactive robot learning. And those are some snippets of interactions that were done as part of my postdoc, where I was controlling one of those robot Kinova arms as a puppet. And then we had the performer robots perform the same thing by shadowing the joint angles. And so we were able to really workshop and do interaction prototyping in a very flexible way. Starting from very sort of simple goal-oriented tasks, such as handovers, where the robot is exploring a grasp, and then when the robot gets it, the person gives a thumbs up to indicate that the robot has done the right thing. Pouring is showing an example of visual gesture-based demonstrations, where the person is telling the robot to either tilt things or shake it when the beans got stuck in the bottle. This is another example of a dynamic task where when the robot gets it, the person gives positive or negative feedback if the robot fails. Example of visual demonstrations using a tool, such as brush strokes. And this can go crazy with creative painting tasks and other kinds of open-ended tasks, potentially involving some creativity. So if we think about this picture of robots learning from humans, what makes a good apprentice? And I asked an apprentice of mine called ChatGPT to tell me about what are some of the characteristics of a good apprentice. And there's a lot of text, but I kind of highlighted the stuff that I think matters. The first one is adaptability, which we talked about quite a bit. But there's also things like curiosity, which interestingly relates to asking questions in addition to kind of exploring and seeking understanding, which is something that we don't often think about in RL, for example. Things like initiative, right? So taking on tasks, but also seeking out opportunities and participating in your own learning. And there's a bunch of other things that are incredible problems for HRI researchers, right? Like things like diligence and persistence, respect, professionalism, humility, right? And those are things that will really matter in an interaction, but are often not thought about when we think about interactive robot learning. I want to finish this part of the talk with a couple of things. The first one is just a quote I found on the internet that said, "Practice alone won't make you an expert. Expertise is contagious. Spending time with people who are willing to invest in you and share their knowledge with you will give you the edge," et cetera, et cetera, et cetera. So you get the point. Before I delve into more technical details of my own research, I would like to leave you with what I believe is a prime example of teacher-learner interactions in a human context. So we'll just take a minute to watch this video, and then we'll talk about it after. Enjoy.
And yes, yeah.
Sotto il buon cielo c'è la
Up here.
cuffietta rosa.
Open.
Se
Open. Now melt.
So this is quite amazing, isn't it? Like, you have a person who has experience teaching, you have a person who's trying to learn, and the way that information is being transmitted between this expert teacher and this apprentice is quite remarkable, right? There's use of touch, there's use of abstract gestures, of verbal utterances, of emotions, right? There's an emotional bonding between them. You feel that they've worked together for a long time. And I can't even begin to think what this would look like a few years from now with robots, and I'm very excited about it. The truth is we're very, very, very far from this in robotics at the moment. So I want to ask a question. What does it take to build robot apprentices? And I want to cover several things today. So I'm going to go through this list. And hopefully by the end of this list, you'll get a sense of how we can potentially make advances in that space of robots as apprentices. So the first obvious thing that we need is better algorithms. I think we all agree on that. And this is work by one of my PhD students, Moo-Han Ho, who's been thinking a lot about how do we actively shape demonstrations, right? So if we tell a person to provide demonstrations to the robot, they oftentimes have no clue what kind of demonstrations would be helpful or what should be the distribution of these demonstrations in some sort of demonstration space. So he's been thinking about how can we actively guide a robot into the right, actively guide a human into giving the right demonstrations in tasks such as, for example, here I'm showing an example of a pepper robot that is tasked to throw this ball into a target landing area, right? So the problem goes like this. Assume you have a distribution that you want to achieve in your demonstration space. You want to have a robot that can actively request the right demonstrations to be able to match that distribution, right? And with his algorithm that accounts for uncertainty in how people respond to certain requests, I was able to show that for 2 tasks that we tested it on, the average deviation from that target distribution was reduced based on that kind of algorithm. So this is kind of a static version of active guidance where you have a number of demonstrations you need to show and you need to somehow match it to a distribution. Taking this a step further, thinking about how these demonstrations could be requested in a process of learning. So if you have a reinforcement learning agent that from time to time goes and asks for demonstrations, this work is looking at making active demonstrations requests during the learning process. So I'm showing here a simple toy example of, well, if I have a fixed goal here and I have my agent starting on the line and it needs to somehow get to the goal as fast as possible, how do we select initial states that allow the agents to learn most efficiently from these demonstrations? And I'm showing one of the examples of the outcome of an algorithm where you can see how this distribution of initial states is actually not uniform, right? So there might be different distributions for different tasks, and this is something that the robot can learn automatically. So the key problem to solve here is, when does the agent query, and what does it query, right? What is the demonstration that it requires at that specific point in time? And the key takeaway is that you might not know unless you're actually learning the task, right? So this is something you might not know a priori as an agent that is learning. So this is an example of a couple examples of algorithms. But algorithms, I would argue, are not the only thing. We need to think about things like teaching modalities, for example. What do I mean by teaching modalities? I'm thinking of new ways that we can actually So untapped potential in how humans naturally interact with robots that could serve as new teaching signals. So let's take a look at this one.
Up, 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 up. No. Up. No. 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 Okay, right. Keep on going. Right, right, right. No, 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 right. Up, up, up. Down.
So prosody, which is everything that's about speech that's not the content of the speech, we argue carries a lot of information about what you want an agent to be doing. And so it boils down to saying that how one speaks is as important as what one says. And in this work, we look at how we can use prosody as a useful teaching signal for an RL agent or reinforcement learning agent to learn better policies, right? We're not changing anything about how the human talks to the agent. We're just tapping into this information that was not used before. So what we did is we mapped these prosodic features, such as pitch, volume or energy, etc., into things that we can quantify from an MDP point of view, MDP metrics, such as Q values, advantage functions, etc., etc. And we also showed that by augmenting simple algorithms like Tamer with the prosody information, we were able to achieve better policies for the learning agent. This is another example. This was one that was inspired by how shepherd dogs use proximity from sheep to be able to teach them how to go along the right trajectory. And we asked the question, well, what if we do that with a robot, right? So if we have robots in our environments, we can potentially use, and people naturally actually use, proximity to the robot to indicate expected behavior of the robot in a navigational task. So this is work by my student Advitya Mandal, who did her master thesis on using proxemics as a teaching signal for a learning agent. And so she designed an interface that would update the path of a robot according to what we call proxemic interventions of the person, using the sensors of the robot base here. And what she was able to show with a small pilot study with 18 participants is that this kind of interface was less cognitively challenging and more intuitive than using things like a joystick, for example. And we see potential applications for this work in things like navigation and dynamic logistic spaces, for personal robots, for elderly care, for example, or in shopping centers. So those are two examples of teaching signals that are just there. They're like low-hanging fruits, and I argue we should take advantage of them because that's kind of free information, right? But what we also need is novel ways of interacting in the first place, right? We need to think about how to design these interactions so that these structures can allow for better information exchange between teacher and learner. And so to this end, we took inspiration from dog training. So we actually went into dog training centers, and we observed how these people train dogs, different kinds of dogs, from puppy training all the way to service dogs. Then we collaborated with an animal behaviorist who was visiting us from the UK and a communication scientist to think about this interaction design problem, right? So how should we design interactions that make it intuitive for people to apply their knowledge about dog training, or at least how dogs behave, and apply that knowledge directly into robots? And so I'm showing here two design vignettes we did. The first one is about this Roomba that is trying to get on a carpet, but that's an area to be avoided. And through this natural interaction, the person is telling the robot to avoid that area by calling its attention, giving negative feedback, giving it a good job, thumbs up, and then eventually the robot learns a flagging for that area. The second one is using luring, using a red ball to lure the robot into the right trajectory. And so this was also inspired by using treats in dogs, right? And also tapping it on the head to say good robot in the end. So this was an interaction design effort, so there was no actual learning happening. We were mostly interested in designing these interactions. And this is stuff that we've briefly published about, but we're currently running some larger scale studies to really evaluate these designs. By the way, this was better than Choreograph if you've used it before with the Now and the Pepper robot. Another source of inspiration for this interaction design problem comes from the field of performing arts, so from puppetry, dance, and theater. What I'm showing here is an installation we did at a festival in Utrecht in the Netherlands, where we had these robots interact with participants in what we call playful tasks. So there were tasks that had no goal whatsoever. There were some actions that were allowed, so kind of like a game. And we saw very interesting interactions unfold as a result of these simple building blocks. What you see here is a bunch of people. There's one person here that is controlling a robot physically by moving it. This is a professional puppeteer. We paid by the hour to control our robot. Those are the performing robots that are basically mimicking or shadowing what the puppeteer is telling this puppet robot to do through wireless transmission. And the two people here are dancers that are investigating nonverbal ways of communicating with these robots. And then you have a student assistant that's sitting there taking notes. So this was a very interesting example of how do we involve different expertise from people who are experts at all sorts of things, from moving things in space, which is puppetry, from interacting with other agents in a creative way, which is dancers, and from people who are researchers, observing these interactions and generating knowledge, together in the same space to do better participatory design, better co-design for these types of interactions. And if you're interested, there's a paper we published about it, and there's also a study we ran that was more about showing that these people actually have implicit knowledge that we can use for HRI. OK, great. So I've talked about interaction design. I would also like to think now about interfaces. And what I mean by interfaces is, given that we have an interaction, given that we have a teaching modality, how do we design actual interfaces that allow us to most efficiently transmit that sort of information from teacher to learner? Let me give you an example. So those are 4 examples of what we call kinesthetic corrections in humans. So I'm sure all of you have experienced, learning how to wash your hands for the first time as a kid. Or if you do yoga, that you have a teacher correcting your asana using their own body by kinesthetic corrections. As a dancer, I very much remember, that I need to lift my elbow when I'm doing ballet. I still have the memory of touch of my teacher. And if you're doing horseback riding, this is exactly the kind of stuff you do with the horses. So we thought, how can we do that with a robot, right? And especially that we have some robots that may not have sensing capabilities to actually sense torque or force, right? So we designed this robot wearable device that's basically a ring that you can put on a robot. And the way it works is that you have 2 rings. One ring is attached to the robot, so it doesn't move with respect to the robot's arm. And then you have an outer ring that is loosely coupled through some springs. So it allows you to actually move and steer the robot in the right way. And then we were able to sense the displacement of this outer ring, both translational and in orientation, with respect to the inner ring, using some magnets on the outer rings and using some magnetosensors on the inner ring. So we were able, from these sensor readings here, to recover the full rotation and translation of that outer ring with respect to the inner ring. And based on that, we implemented a very simple controller that allowed the person to correct the trajectory. And what we saw is that the completion time was significantly lower with this kind of system than with using a keyboard, for example. It also turned out to be more usable and requiring comparable task loads according to a NASA TLX. This is work we published at ICRA last year, so if you're interested, feel free to look at the QR code. OK, great. So now I've shown an example of what I think about as an interface. The next thing I want to talk about is understanding the user. And I think if you're an HRI researcher, you pretty much understand that understanding a user is very important. And so I'll just give you an example of what it means for us to think about an understanding of the user in this specific context. So some of the work in that space that we've been looking at with some master's students is, how do we look at teacher behavior, right? How do we model different ways that people would want to teach robots? This is a study that Konstantinos did during his master's thesis, where he built a multimodal teaching system that included 3 modalities. The first one is you get to choose the starting position of the agent every episode. You get to demonstrate actions. So you can decide when to intervene and for how long to give the actions in the trajectory. Then you can also give it binary feedback, so either good job or bad job. And this is the interface we had here with some action buttons and some feedback buttons here. And we ran this in a simulated simple reaching tasks kind of scenario, right? So we had the panda arm in simulation, and we studied how people made choices about how to actually intervene and when to intervene. And what we saw in a study we did with 58 participants is that things like gender, for example, had an impact on the teaching behavior, right? And we're currently looking at other types of demographics. But this is just an example that shows that there's no way that we can design a single model that will work to capture all the variations that is there in how people teach, and that we should look at individual models of teacher behaviors, or at least profiles of teachers. The other thing we did is that we asked people how their actions related to, so what are the factors that influence how people made decisions about teaching? And this is some of the open-ended responses that we've coded, and we're doing a follow-up study on that to see in different kinds of tasks if this distribution actually changes. Again, I'm not going into details. If you're interested, there's an LBR we just published at HRI last week. All right, so we've talked about a lot of things, right? We've talked about algorithms. We've talked about teaching modalities, teaching interactions, interfaces, and now understanding of the user. The last bit that I would like to cover today, I think, is one of the most important bits. And that's what I call teacher-learner synergy. So what do I mean by synergy in this context? Well, I mentioned the fact that the teacher is not a source of information, right? The teacher is more than that. And I strongly believe that when we think about teacher and learner, we shouldn't think of them as two agents interacting. We should think of them as a system, right, that works together. And that relates back to the idea of hybrid intelligence that I talked about before. So how do we think about the system, right, that interacts together, and how can we improve it? So this is work by my PhD student Bernhard Hilpert, who's looking at how to create learner-to-teacher feedback that could potentially improve teaching, right? So if you look at this interaction diagram here, what we're really interested in is this arrow from the robot back to the teacher that would give useful feedback signals that are grounded in an RL process. So if you have an RL agent, it's able to somehow, based on this RL process, express those signals, and we're hoping these signals would be useful to actually help the teacher teach better. So 3 things here. The first one is, what are actually these learning states of the robot that might be interesting in the first place for teachers, right, as feedback? Right? So we're currently running an observational studies to understand what are these states and how they might be useful in a teaching task. Once we know these states, the second question would be, how can we represent these states and how can we express them legibly to a teacher, right? And then once we have that, we hope that we can answer the last question, which is, can these resulting signals actually improve teaching quality, right? Can it guide the teacher to teach in a better way, in a more efficient way, or in other words, improve their teaching policy? Fantastic. So this was the last technical slide that I had, pseudo-technical. I would like to end this talk with some wishes. So my first wish is for us to build the next generation of robot apprentices. Hopefully by the end of this talk, you can see the value of doing that. My second wish is to do it together with a diverse set of disciplines. And hopefully by the end of this talk, you also see the value of collaboration in this space, but also in HRI as a whole. My third wish is for us to be critical on the use and potential misuse of new robotics technologies in given contexts. And the last one is to make it fun, to make it personal, and to make it a community-driven journey. So with that, I'd like to thank you, and I'd like to quickly say that if you're interested in an internship, please shoot me an email. We might be able to arrange something. I want to thank Henny one more time and all of you for being here today. And I'm very happy to hear any thoughts, comments, or questions. Thank you very much.
Thanks so much for the talk, and nice to see you again. You talk a lot about observing, adding these different type of interactive elements during the training. But what about during execution? So I'm imagining we have autonomous cars, they're trained, there's all this fancy stuff that goes into training on trajectories and human learned behavior. But imagine a car that has a passenger in the back seat, it's about to hit someone, they yell no. So similar sorts of interactions kept in the loop during execution. Have you looked at those at all, or studied them in some of the applications you've looked?
Yeah, no, thanks for the question. I think this very much relates to the boundary between kind of interactive learning and shared control, right? And I would say these overlap in a sense that, in some cases, so I've actually shown quite a few examples of what I thought would be algorithms that would be used at execution time, right? So there's an instant of an execution, and you're intervening in some way, and then you have an immediate response of the robot, like, for example, this example of intervening using Proxemics, right, getting close to the robot, that the robot would immediately correct its trajectory, right? It wouldn't just learn from it and do it better next time. It would immediately correct for it. Similar thing with the example of the steering wheel for the robot arm, this little device we did. This would be an example of, like, imagine you're in your car that you would actually intervene into the actual during execution, right? So I think these are closely related. I think there's a lot of interactive reinforcement learning algorithms where, the robot will learn eventually, but it's not a priority for it to act upon that intervention right away. And I think this is where a lot of the literature on shared control could be useful to think about how can we ensure that we have kind of safe behavior in the moment, right? But also how can we learn from it? And I think the learning part is a layer you can add on any other algorithm where you say, hey, I had a user intervene, and given that information, you could potentially do better next time if you have your context variables or some sort of similar situation in the future. Yeah.
So I really loved your talk. I loved all the visuals, all the examples. And what stood out to me is that a lot of the interactions are leveraging modes of communication that are natural for humans, like speech, like touch and movement, etc. And I think that's something that's really cool about robotics, is that they're able to interact with us in ways that humans can't in their human-to-human interactions. Like robots are able to use like projectors to display maybe their internal states, etc. So have you also thought about ways that we could communicate with robots in ways that go beyond just human-to-human interactions?
Yeah, that's a really interesting one. During my master's thesis, I worked on lights as a way of communicating internal state of robots. That's not something I've been doing a lot recently with my work. I think I've been just so fascinated by how humans interact together that I've kind of like started exploring that. But definitely I think things like haptics could play a big role, like vibrations and things like that, right? So things that are, so designing usable interfaces that are not necessarily natural ones, right? In the sense that they don't match how humans naturally interact, but they would still be very usable. Like, unlocking your phone is it's a very intuitive way, it's a very usable way of doing it, but it has nothing to do with what it does even unlocking a person mean. That I don't even know if that's a thing, right? So yeah, usability is definitely the kind of end goal. It's a very broad concept, and within that there is naturalness, intuitiveness, and other things. And I think at the moment I don't have clear examples of things that are robot specific to share. But thanks for something to think about. Yeah.
There, like especially like the example with the teaching, right, with the singer. There's also usually like a lot of explanation going on of like not just like, okay, do this, do that, but also like, okay, why, right? Like why is this done? Like, are you looking at that part kind of like also from some direction? Because sometimes, sure, we can push the robots over and be like, okay, go there, right? But that doesn't necessarily mean that they like subsequently understand why they have been given that advice, right?
Yeah, thanks for that. So I think a lot of the work on learning from explanations is done in the context of language instructions, of saying, you did that, and that was good because of that, or and there's also literature on looking at using features that explain a certain intervention, right? Say, I did this, so I intervene in this way, or this is how you should behave as a robot, and this is the feature that matters here. So you kind of give it a hint on what is that feature to look at. I have a colleague, there's a colleague of mine, Sylvia Tully, she's working on that kind of stuff at the moment, learning from explanations. So you give feedback, you give whether it's corrective, evaluative, whatever, and you give a reason why, right? It's definitely, I think, something that could be extremely useful for the learning agent in terms of like capturing a lot of information in a very compact way. In certain cases, it might be that people don't actually know why, right? In some cases, right? So for example, if you want to tell there's this example that I love. It's a articulated weird thing. It's a RL agent that has a lot of joints, and it's trying to learn how to do a backflip, right? So it tries to do the backflip, and sometimes you're like, I have no clue what this is about, and people, give it feedback, compare trajectories, and they do it pretty well. If you see, two attempts and one gets closer, you probably know that one gets closer, and eventually it learns it. Yeah, in that case, I'm not sure. I mean, you could say not enough power or things like this, but it becomes very difficult to tell it like this is why you're failing or this is what you're supposed to do because you have no clue. You know it when you see it.
Also like an alignment between how the robot perceives the world versus you, right? Like your why might be very different from the robot's why.
Yeah, so in learning demonstrations, I call this the correspondence problem, right? But also for evaluating your own, appraising your own performance, there might be a huge mismatch there. So I think in some cases, definitely, this kind of intelligence might be extremely helpful. In other cases, it might not be very usable. So it's good to think. There's a huge ton, like a whole ton of methods. And I think, most people working on that are usually on the language side of things. But thanks for the question. Yeah.
I was also fascinated by this particular interaction. And one thing I noticed in it is that there's a lot of use of metaphor for communicating, right? So she's doing the tremolo by shaking her hand, and she's doing the scales by stirring the pot or whatever. Have you looked at all at how people use metaphor, and how that robots are supposed to even understand that in their learning interactions?
I have not, and I think that's a really, really cool area to explore. There's a bunch of people working on social signal processing, and they're all about, taking these abstract observations or behaviors and trying to extract some latent variables or representations. There's one project we did where we looked at personalizing gestures to control a robot. So where people would kind of say, if I want the robot to do this, this is the kind of gesture I would do, and it would learn a mapping. But it was a purely supervised learning thing where you would just label some examples and then you would learn that. But you could imagine that a robot could learn a grounding from these abstract gestures that arise naturally into something that the person could demonstrate on the robot, for example, which would make it more personalized. But I think there's indeed something more universal about how we use metaphors that potentially LLMs could solve one day. So let's see. Yeah, I also thought, I think we should all retire next week probably, but yeah. Any other questions?
I have questions. You talk about different ways. First of all, good talk. Thank you. You talk about different ways of, things that should, we need to think about to build better robot apprentices, like algorithms, modalities, interfaces, interactions, etc. If you had to choose one or two, which would you think is would have the most impact in coming up with better robot apprentices?
So I would say this is maybe a bigger one. So I would say that one, the teacher-learner synergy. I think that's really, I think, teaching interactions, people in design could really help there. Interfaces, it could be a combination of HCI, people, other things, but I think the teacher-learner synergy is something that as an HRI community, we were the most qualified to think about. And so for myself, I would say that's probably the one that I would say is most important, because there's a lot of early work from Andrea Tomas and colleagues on things like transparency influencing teaching, right? That if you have a robot that is transparent about its process or expresses things like confusion or hesitation, that it really helps the teacher, right? And this was just scratching the surface, right? There's so much more about how we do things that, so even as a teacher, you look at your students' facial expressions, right, to adjust your teaching and that kind of stuff, right? So I think there's a lot to do. This is maybe 10 bullet points in one, but I would probably pick that one. And I think the rest is already, we know more or less where things are going, more or less, maybe not But that one is a bit of a tough one, and I think it can have a big impact. So I would personally choose that one. Yeah?
I was just curious, are there any self-driving car companies taking feedback from their, like the people taking rides? Because I often have a lot of feedback from them.
I know a lot of work on imitation learning for self-driving cars and that kind of stuff, learning kind of personalized models of driving, that kind of stuff. I personally haven't seen any work on online learning in that context. I don't know if you've encountered any, but yeah. So yeah, that would be very interesting. Also to think about safety critical situations, right? And also when to provide feedback. Do you provide it at the end of the episode, during the episode? Does it react upon it or not? So those are all, I think, questions to keep in mind also in terms of safety and usability as well as algorithms. So, thanks.